Welcome everyone to another AIST webinar. This is webinar number 6, the Pathways to Blast Furnace-Based Decarbonization. Our team, sponsored by the AIST Decarbonization Subcommittee, has been working diligently to bring our moderators and presenters today for you to enjoy both live and later if you want to return with the web recording. We have, thankfully and gratefully, a sponsor, Leckler, who is proud to sponsor this webinar and is a leader in engineered spray applications for the steel industry with expertise in optimizing gas-liquid interactions. And Leckler delivers advanced solutions for carbon capture and blast furnace processes, enhanced mass and heat transfer efficiency, and their innovation spray technology is designed to reduce emissions, improve performance, and drive sustainability. Trust Leckler to lead the way in spray applications and carbon capture solutions for the steel industry. My name is Charlie Bender, and I'm the staff engineer, and I want to just go over a couple of quick AIST webinar guidelines. Your audio has been disabled. If you have questions, please put them through the Zoom software in the Q&A feature, which will present the questions to our moderator and presentation team. Our host and moderator will determine which questions are presented during the live webinar. In the end, if there are questions that aren't answered, we will return through contact after the webinar to finish up the questions and answers. This session is being recorded and will be available on demand in the replay section of the AIST website. Prohibited, please. Photos and recordings of this presentation is prohibited. If you have technical difficulties, please email training@aist.org during this webinar for resolution. AIST also has an antitrust guideline. We do not encourage price fixing. There are several items in our antitrust guidelines, and they are enforcing the United States antitrust laws. AIST also has an anti-harassment policy where we're really encouraging a comfortable meeting and attendance by everyone in our audience. If you have questions, again, please look to the bottom of your Zoom software and type the questions into the Q&A box. And should you have technical difficulties, return to an email system to training@aist.org. The AIST decarbonization webinars have been going on for some 3 to 4 years now. You can find them all in the past webinar area. I'd like to take the opportunity today to introduce our moderators, both Madhu Renate and Joe Mori. Excuse me. Madhu Renate is General Manager of the Raw Materials Strategy and Supply at Steel Dynamics. He has primary steelmaking advisory services specializing in assisting companies that reduce their, my mistake, sorry. Mr. Madhu Renate is General Manager of the Raw Material Strategy and Supply for Steel Dynamics Flat Roll, USA. Madhu joined Steel Dynamics after more than 30 years of career with ArcelorMittal and its predecessor companies. He started his career in Inland Steel R&D Division at East Chicago, Indiana, working on raw materials, iron making, and steel making. He progressed through technical, operational, managerial, and leadership roles and ran the Indiana Harbor Works and Burns Harbor Works as Vice President of ArcelorMittal. He switched to the mini mill section in 2013, successfully running Steel Dynamics' modern electric furnace mini mill as VP and General Manager until 2021. Early in Madhu's career, AIST recognized his significant contributions to the raw materials and iron making industry with its J.E. Johnson Award and T.L. Joseph Award. Recently, AIST appointed Madhu as its distinguished member and fellow. Madhu is an active member of the AIST Decarbonization Subcommittee, and he earned his master's degree in materials science and mineral engineering from the University of California, Berkeley, and a bachelor's in metallurgical engineering from the Indian Institute of Technology, Mumbai. Our other moderator, Mr. Joe Mori, will have his contact information on the screen in just a minute. He is the owner of Mori Industrial Consulting, and provides primary steelmaking advisory services specializing in assisting companies reduce their carbon footprint at the best overall cost and value. Joe's current client list includes Limelight Steel and Helios, two companies poised to make a large impact in the effort. Joe has over 28 years of international experience in the primary steelmaking process, from coke making to slab casting, with U.S. Steel spending most of his time focused on blast furnace iron making. Joe began to shift his focus to include greenhouse gas reduction in 2020 when he became the tactical lead for greenhouse gas reduction for U.S. Steel. During this period, he became very active in several organizations that have significant contributions to this space, including the Steel Manufacturing Simulation and Visualization Consortium with Purdue Northwest and the INDABA partnership with Carnegie Mellon and the AIST Decarbonization Subcommittee. Joe was the AIST Iron Making Technical Committee lead in 2023 and is a current member of the Board of Directors of AIST through 2025. At this point, I'd like to introduce very quickly Mr. Felix Fischbach, who is Vice Chair of the AIST Decarbonization Subcommittee, for a quick description of the overall webinar series.
Thank you very much, Charlie. So I'm speaking on behalf of the Decarbonization Subcommittee of the AIST. Our subcommittee belongs to the Energies and Utilities Technical Committee. We have been established in 2021. And with all our endeavors, we try to discover a bit more topics regarding decarbonization and try to unveil a little bit more what is below the surface, below all those polished presentations about a beautiful decarbonized steel industry future, and try to dig in what is the technical reality and what we can do in the future. Today is the 7th seminar, and I thank all the moderators and speakers, and especially and also AIST, to make this happen, to participate today, to organize all this. Thank you very much, Madhu, Joe, and all the presenters. And just quickly, a word of advertisement for our next webinar on November 26th. The title will be Ironing Out Carbon, the EAF and DRI Revolution. The moderators will be Michel Vachon from Big River, Kyle Vanova from Steel Dynamics. And we will have two speakers, Dennis Hennessy from Staker, which was H2 Green Steel, about their technology, and Jeremy Jones from Continuous Improvement Experts on the challenges of DRI utilization in steelmaking. Thank you very much. And please, everyone, moderators, speakers, and participants, enjoy this webinar. Thank you.
Thank you for that quick introduction, Felix. I want to note that people are already starting to use the Q&A section of this live webinar. And I want to turn the presentation over to Joe Morey, who has a few minutes of description of the overall webinar. Joe?
Good morning, everybody. Let me share my screen here. Thanks for joining this webinar. The Iron Making Technical Committee and the Decarbonization Committee were very keen on this topic, as a lot of discussion has been made on alternative solutions to making iron for the steel industry. And we wanted to bring the focus back to the blast furnace. And I'm going to show you a few reasons why with these slides. Okay, the title of our presentation is going to be Pathways to Blast Furnace Decarbonization. This is kind of a joint process between the Iron Making Technical Committee and the Decarbonization Subcommittee. When I put these slides together, it was very kind of blown away, with all the discussion that we've had with greenhouse gas reduction over the years. I thought for sure we would have had some, slight reduction in the greenhouse gas emissions from the steel industry with all of the efforts that have been going on. But if you take a look, From 2007 to 2022, the level of greenhouse gas intensity has gone up in the world by 5%. And part of the reason why is, blast furnaces are just continuing to be part of this discussion. This 72% of all the steel produced, according to World Steel in 2022, this is the numbers I got for this, were made by the blast furnace route. And you can look at the link there with kind of the descriptions of what's happening there. And you can see here, blast furnaces are still under development in China, India, Vietnam, and Malaysia. So this is just getting a bigger and bigger issue, and iron making and steel making is continue to contribute to this greenhouse gas. So as the Iron Making Technical Committee and the Decarbonization Subcommittee, we decided let's focus also on the blast furnace process. And so just to let you know what this is going to be talking about, this is the first of two presentations that we're going to have. We're going to focus on this ore mining and pellet and sintering ore process today, and then also somewhat on the blast furnace process today. So we're covering this whole, eventually we're going to cover this whole value chain, coal mining, all the way through the oxygen steel furnace as it relates to decarbonization. You can see this blast furnace process is 1.476 on the average in 2022, tons of CO2 per ton of liquid steel. And that's because a great portion of this also gets turned into electricity. And some people actually even flare this blast furnace gas that gets generated by the blast furnace. So that's the end of my presentation. If there's any questions, you can put those in the Q&A. We're going to focus on, I'm going to pass it over to Madhu. We'll introduce our next presenter.
Thank you, Joe. While Joe Poromo is bringing up his presentation, I will do the introduction. I've known Joe for several years. Joe is going to talk about blast furnace metallics. Dr. Poromo got his master's and PhD degree from Center of Process Metallurgy from State University of New York in Buffalo. He began his career at Bethlehem's Homer Research Lab in 1993 in raw materials and iron making area. In 1993, he established his consultancy, Raw Materials and Iron Making Global Consulting. Through 2008, his principal client was Quebec Cartier Mining Company, where he served as a director of technology for international business. Currently, he consults on steel, iron ore, and other natural resources for technology providers, financial and consulting companies on a global basis. Dr. Poromo is a distinguished member of AIST, and his awards include T.L. Joseph Award for longstanding contributions to iron making technology and the Poromo Symposium for sustainable iron making and steel making. He is also a special member of the International Iron Metallics Association. So I give you Joe Poromo. Joe?
Okay, thank you, Madhu. Is my presentation showing up full screen for everybody?
Yes.
Yes, sir.
Oh,
Yes.
great. Okay. Yeah, I'm Joe Poromo. My contact information is shown here. If you want a copy of the presentation, please send me an email. Or if you have any other questions that aren't answered, you can also send me these questions via email. So on the following slide, I have the agenda. Now I'm trying to advance the slides here. Then, oh, here we go. Okay, yeah. I'll basically start out by talking about the role of the raw material processes and overall blast furnace BOF CO2 emissions. I'll comment on the greenhouse gas differences between pellets and sintering, specifically talking about the pelletizing of magnetite ore versus hematite ore. I'll also touch on the mining emissions that happen back at the coal mine and the iron ore mines. Say a few words about the use of lump ore and also the coal briquetting processes. I'll make a comparison between flux versus acid pellets at the pellet plant and in the blast furnace. I'll say something about decreasing the silica level of the iron ore going into the blast furnace via increased beneficiation at the iron ore mine. And then I'll give a listing of opportunities for CO2 emission reductions at both the sinter plant and the pellet plant. So on the following slide, we're looking at the overall blast furnace BOF process. What we want to focus on, if we look at the blast furnace itself, we see the big number for CO2 emissions is at the blast furnace, 1,476 kilograms of CO2 per ton of hot metal. This is obviously a much bigger number than we see in the raw material steps. Sintering 260, pelletizing 35 kilograms, coke making 97. Now, of course, we see sintering is almost 10 times that of pelletizing. Now, here in North America, we're fortunate we rely mainly on the pelletizing process with a much lower CO2 footprint, but most of the world really relies on the sintering process. So there has to be some much more attention paid to CO2 reduction in the sintering process. So this gives us the overview. And on the following slide, we're looking at reducing energy consumption on a global basis. The number I showed in the previous slide really pertains to the right-hand part of the slide, where most of the world's blast furnace iron making has a total reduction rate in the vicinity of 500 kilograms per ton of hot metal. But we see on the far left of the slide, countries like India, Ukraine, and China, much higher reducing rates. So therefore, the CO2 emission number would be much higher for those operations. Now, of course, this data is somewhat old, but if we were to take this data now, we would still see the same relative distribution. Perhaps the reduction rates would not be as higher in the countries on the far left. So we have to keep that in mind as we look at CO2 emission levels in blast furnace iron making. Turning now to the mining process, both coal mining and iron ore mining. At the top of this slide, we're looking at coal mining, and we say the coal mining, the greenhouse gas emissions are mainly due to methane gas emissions. Now, of course, methane is a much more potent greenhouse gas compared to CO2. We also see there's big differences between the type of coal mining that we're practicing, somewhat lower emission levels for open pit coal mining that we would have in Australia. If we look at iron ore mining, we see in general these numbers are much lower than the coal mining numbers. And of course, in iron ore mining, we're mainly talking about CO2 emissions associated with use of electrical power and fuel use in mobile equipment, and also in the beneficiation facilities. We see differences also between the various types of iron ore products that we're mining. Now, of course, both coal and iron ore also have to be shipped. If I can go back to the slide, the shipping modes have big differences in CO2 emissions. We're looking at grams of CO2 per ton on a kilometer basis. And we see the lowest CO2 emissions are for sea freight, somewhat higher for rail freight, and much higher for trucking. And if we look at, for example, examples 1 and 2 down here, if we ship 1 million tons of iron ore, let's say from the Iron Range to a Great Lakes, a steel plant on the Great Lakes, we're talking about 13,000 tons of CO2 for 1 million tons of iron ore shipping by vessel. However, shipping the same amount of ore by rail from the iron ore mine itself to the shipping port is actually a much higher number, even for a much shorter distance, 20,000 tons of CO2 for 1 million tons of iron ore if shipped by truck. So transportation also plays a role in the CO2 emissions scenario. Now, looking at iron ore itself, it also depends what type of iron ore we're talking about. These are data put together by the folks at the Rio Tinto, kilograms of CO2 per dry ton of iron ore. For their mining of direct shipping ores in Pilbara region of Western Australia, that is the mining of sintering ore, fines, and lump ore, we have a very low number. If we look at the Rio Tinto operations in Canada, the iron ore company in Canada, where they have to upgrade lower grade ore by magnetic and hydraulic methods, we see a much higher CO2 footprint, but still much lower than that for coal mining and other aspects. So the type of iron ore does make a difference. Now, in talking about lump ore now, the use of lumpwood does minimize CO2 emissions because we don't have any beneficiation and no agglomeration processes. And if we use the lumpwood in the blast furnace at moderate or low levels, perhaps less than 15%, we would have a CO2 emission reduction. However, if we go to much higher lumpwood rates in the blast furnace, that would increase the blast furnace coke rate and therefore increase the CO2 emissions. Now, we won't say much more about this because the global seaborne supply of lumpwood in the Atlantic Basin is somewhat limited. We'll turn our attention now to the briquetting process. We can say that the use of so-called coal-bonded briquettes are a potential alternative to sinter or pellets because the sintering and pelletizing processes both require energy-intensive induration at high temperatures. By comparison, the briquetting processes have a lower capital cost and much lower energy requirements. So they would appear to be greener alternatives. However, up till now, it's been difficult to produce briquettes with the required physical and metallurgical properties to be able to use them at higher percentages. Their use has mainly been at 5% or less of the blast furnace burden. But in the past year or so, Valley has announced the successful development of their coal-bonded briquetting process. In fact, they're converting 2 of their pelletizing plants to a briquette production. Valley, in cooperation with steel companies in Brazil and elsewhere, they have conducted blast furnace testing in large and medium-sized blast furnaces, and they've shown that such briquettes can replace up to 20% or perhaps more of the blast furnace burden, mainly replacing pellets and sinter. So Valley has begun commercial shipments this year. So the full extent of their applications will become clear in the next year or so. Now, we also have to mention that the briquettes that are produced, they can be produced using either iron ore fines or the in-plant waste oxides, such as dust, sludges, and mill scale. So perhaps the briquetting process can replace the recycling role that the sintering process performs on a worldwide basis. At the present time, we also have to mention, besides Valley, other companies are also proposing similar briquetting technology. So we'll hear more about that in the future. Okay, turning now to the sintering process and what can we do to reduce the CO2 footprint in the sintering process. Well, we can start out by replacing a portion of the carbon that's used in the sintering process. This carbon is usually coke grease or anthracite fines. The possibility of replacing this with biomass fuel, experimentation is already ongoing in Brazil and elsewhere, perhaps partial replacement by charcoal or other biomass sources. We could also talk about utilizing green hydrogen as the ignition furnace fuel, but so far hydrogen is really too expensive for sinter plant or other use. And some of the presenters that will follow will talk a lot more about hydrogen use in the iron making process. We can also talk about switching to electricity generated from renewable sources, so-called green electricity for fans and drives and so forth. Now, green electricity should be increasingly available as renewable sources increase their role in global energy production. Some other things we can do at the sinter plant is shown here, utilizing blast furnace gas as ignition furnace fuel, selective waste gas recirculation, waste heat recovery from circular coolers. Now, the folks at Prime Metals have put together these numbers in parentheses, basically a percentage of CO2 emission reduction associated with each process, and sort of an overview of how this fits into the sintering process. Folks at Prime Metals on the far left of this slide show that for the agglomeration processes, putting all these things together, we can perhaps reduce the CO2 footprint of the agglomeration processes by about 25%. So that's still significant, particularly for the sintering process where we're starting out at 260 kilograms of CO2 per ton of sinter. Okay, turning now to the pelletizing process. If we're pelletizing hematite ore, we can also start out by talking about replacing the carbon additions in that indurating process. And once again, the carbon additions here typically have been coke grease and anthracite. We can talk about replacing these carbon sources with biomass, particularly the use of charcoal is experimental work is ongoing in Brazil with this. But now the typical coal utilization rates are typically in the range of 10 to 25 kilograms per ton of pellets. So there is some good potential for CO2 emission reduction here. Now, we also have to talk about if we're pelletizing magnetite versus hematite. If we're pelletizing a magnetite, we have the exothermic oxidation of magnetite at the beginning of the innervating process. And this generates a lot of energy. It generates up to 40% of the total energy needed in the innervation process. So if we look at the comparison of CO2 emission reductions between magnetite ore and hematite ore, we can see for magnetite ore, it's nearly 50% lower compared to pelletizing hematite ore. And of course, here in North America, we're fortunate that we're basically pelletizing magnetite ores. All the pellet plants are magnetite, except for the Tilden plant in Michigan, that is in fact pelletizing hematite ore. Now, other things we can do with the pelletizing process is shown here. Once again, we can talk about green hydrogen when it's available. And in terms of the burners in the innervating process, the use of plasma torches is also being experimented upon, particularly if the plasma is generated using green electricity. Now, a supplier of such plasma torches, the company called Pyrogenesis, they have a power plant program with a major pellet producer to develop this. And of course, once again, with pelletizing, we can also talk about switching to green electricity for the fans and drives, similar to what we spoke about for the sintering plant. Okay, in the following slide, we talk about some work I did some 25 years ago with QCM. We basically looked at greenhouse gas emissions, comparing flux pellet production to acid pellet production. We looked at the Canadian pellet plants, QCM, IOC, and Wabash. And basically, if you look at the pellet plant itself, whenever we're producing flux pellets, because of the need to calcine the fluxes in the pelletizing process, we actually increase the CO2 emissions at the pellet plant whenever we produce flux pellets compared to acid pellets. However, when we use these flux pellets at the blast furnace, we realize coke rate reductions and also a decrease in blast furnace raw flux calcination. That is the limestone and dolomite. We don't have to calcine that in the blast furnace. So the CO2 emission reductions associated with these two activities is significant. So that we have a net benefit. If we take the pellet plant and blast furnace together, we basically save 65 kilograms of CO2 per ton of pellets by producing and utilizing flux pellets in the blast furnace process, which is quite common here in North America. Okay, the next topic we want to talk about is basically decreasing the silica going into the blast furnace. So we say that by reducing the silica in the sintering or the pellet feed at the mine, we can therefore reduce the silica level in the sinter or pellets going in the blast furnace. This will reduce the blast furnace slag volume, the coke rate, and therefore the CO2 emissions. And we can basically use this observation to justify investments at the mine. That is improving beneficiation, perhaps to increase grinding, installing a flotation process or other means. However, the overall mine and beneficiation economics will still force halting beneficiation at a point where the iron recovery drops sharply, because we have to really look at the beneficiation curve, where we observe that as beneficiation increases, the iron recovery decreases. An example of this is shown in the following slide. We basically see that as we go towards lower and lower silica levels, the iron recovery is dropping. Now, this happens to be a pretty smooth recovery curve, but some of these recovery curves can be pretty sharp, that if we go to lower beneficiation levels, the recovery drops off really sharply. In that case, we have to stop before we get to that point. So that's really a look at the overall possibility of this. So this basically concludes my formal presentation. I do have an appendix which has my presentation from 2021 on CO2 emissions associated with blast furnace reductants. But of course, you're going to hear an update on that from the following presenters. So now if I can stop sharing, or if I can go to the questions, if I can find them now, I can try and answer the questions, or the moderators can pose the questions to me. But thank you.
Thank you, Joe. I think there's just one question out here in the Q&A box, and if there's any other further questions, you can type those in there, and we'll get those answers to you guys. But I have an anonymous attendee who says, "Can you confirm the number for the coal mining? Are those in grams of CO2 per ton of coal or kilograms CO2 per ton of coal?"
I think they were grams, I believe. But I don't have the slides anymore, so I can't see it. Whatever the slide said it is what it is. But I can always check that further and get back to that person if they send me the information.
Yeah, okay, we'll check that. Okay, well, let's go ahead and move on to the next presenter. We have Ian Cameron and Nicholas Aubrey from Hatch. Ian Cameron is the principal metallurgist at Hatch Limited. He develops client-focused solutions to produce iron and steel, starting from basic raw materials, and with an increasing focus on green technologies. His experience includes iron ore processing, blast furnace design and operations, novel iron-making technologies that reduce greenhouse gas emissions. Ian is the lead author of a new book, Blast Furnace Iron-Making Analysis, Control, and Optimization, where he and his co-authors outline a first principles approach to complete blast furnace heat and mass balances. Ian is a 4-time winner of the Association of Iron and Steel Technology Joseph S. Capitan Award for the best paper in the iron making division, and the 2023 Hunt Kelly Outstanding Paper Award, second place for his paper on reducing blast furnace carbon emissions using scrap and reduced iron additions. Ian was further recognized by the AIST, winning the Thomas L. Joseph Award and Benjamin in 2022, and 2023 he won the Benjamin F. Fairless Award for distinguished contributions to iron making technology. 2024, Ian won the Tech Sustainability Award from METSOC, the Canadian Metallurgy Society, for his work on steel decarbonization and recognizing his efforts to effect positive change. Ian holds a bachelor and master's degree in metallurgical engineering from McGill University and is a professional engineer in Ontario. Nicholas Aubrey is a process engineer in Hatch's pyrometallurgy sector practice. His experience includes iron and steel making project work, focusing on blast furnace iron making, benchmarking, modeling, optimization, and continuous improvement. He has a passion for solving some of the biggest challenges facing the iron and steel industry, namely trying to reduce the carbon intensity of iron and steel making. Nick has satisfied his passion by helping clients understand their options to reduce emissions, be it assessing incremental changes to their iron making process or working to understand the transformational changes to achieve long-term near zero emissions goal. Nick has a Bachelor of Engineering in Chemical Engineering and Management from McMaster University and is a professional engineer in Ontario. Nick?
Thank you, Joe, for the introduction. This morning, I'm Ian Cameron from Hatch. This morning, my colleague Nick and I will go through changes in the blast furnace that we can consider to reduce carbon emissions. Today's agenda, we'll talk about 5 topics: alternative fuel injection, biomass usage in the blast furnace, the use of alternative iron units, principally scrap and direct reduced iron, electrification tools, and lastly, transformational changes that can be considered. So my colleague Nick is going to go through alternative fuels.
Yeah, thanks, Ian. So we're talking about alternative fuels. Really what we're trying to do is replace some of the carbon used in a blast furnace with hydrogen. However, as you can see on this graph, when considering this, you need to account for the change in the energy balance within the furnace as you change the fuels. And as you increase the amount of hydrogen, the impact, the temperature impact, as shown by the green line, increases quite a bit, and that's largely driven by the effect of dissociation as you get more hydrogen into the furnace. So we're talking about hydrogen specifically, and that's pure hydrogen injection. The figure on the right is what we call an operating window. When you start injecting hydrogen into the furnace, you need to balance the impact it has on the flame temperature in the furnace and the top gas temperature at the top. And in order to satisfy both constraints, you need to adjust the oxygen enrichment and the amount of hydrogen you're injecting. And as you can see, when you're injecting hydrogen, the operating window is shown in red, labeled with a 1 there. The operating window does get quite narrow, and the balance in the furnace needs to be tightly managed. And from our analysis, we believe you can get up to about 35 kilograms of hydrogen injected into the furnace before you start running into issues. However, that would be a theoretical ideal case. Likely you'd want to dial that back a bit to around 30 kilograms to give you a little bit of flexibility to adjust normal process condition changes. So that was our analysis, and then comparing that to some of the literature that's been published elsewhere. ThyssenKrupp in Europe has actually done some trials on hydrogen injection, and this graph shows some of their results. So this graph has quite a bit going on, but essentially in the top right is their starting point, where they had 0 kilograms of hydrogen injection, their base coke rate of 311, and then that sharp decline going from the top right down to the bottom there, they were able to trade off PCI for hydrogen injection, which drastically reduced their emission intensity. Once they reached that point, though, they found that to increase hydrogen even further, from that 23 kilograms that they were achieving there, they had to add a coke in addition to hydrogen to replace PCI in order to maintain the heat balance in the furnace, which reduced the amount of CO2 emission reduction per unit of hydrogen injected. And what they came out with in the final conclusion was that about 27 kilograms of hydrogen could be injected, which aligned pretty nicely with our analysis, which was good to see. So to conclude, looking at hydrogen as an alternative fuel, this graph is a graph we like to use to show the impact of the emission intensity, and essentially what it is it's trying to control for boundary conditions for different operating routes. So on the x-axis you have the amount of scrap used in the final steel product, and on the y-axis you have the emission intensity of the steel produced. And then the yellow boxes are the typical operating ranges. So looking at the top left, where we're focused here, is the integrated steel making route. We believe that the emission reduction that can be achieved by a simple addition of hydrogen to the blast furnace as a alternative reductant is about 20% of the total emissions, which while it doesn't get you down to zero, it is quite a significant improvement, and it's worth evaluating further. So that wraps up the discussion on alternative fuels, and I'll pass it back to my colleague Ian to talk about another alternative fuel, which is biomass.
So in this slide, we can see a picture, a flow graph of the biomass value chain. So biomass is waste wood, waste agricultural waste that are available. They contain a lot of moisture. So the first thing you have to do is dry the biomass before continuing. Then pyrolysis of the biomass is heating the biomass in an oxygen-free atmosphere to produce 3 products: biocarbon, pyrolysis liquid, tars, and oils that are produced during the pyrolysis process, and a syngas, a carbon monoxide hydrogen mixture. The degree of pyrolysis is quite important for the end use. In the blast furnace, if we're going to inject it as a PCI replacement, we can tolerate quite a bit of volatile matter in the biocarbon, which reduces the amount of pyrolysis liquids and syngases. In some other applications, and I'll talk about bio-nut coke or use of biocarbon in the electric arc furnace, we might need a much higher carbon content, which produces more pyrolysis liquids and syngas. The pyrolysis processes are fairly mature and at low capacity at this stage of the game, and I would say it's one of the big obstacles towards using biomass. The other is the logistics of getting the biomass to the steelworks, which is quite considerable. It's very light, it contains a lot of water, and usually is often far away from the steel production sites. If we look at the use of the biomass in the steel value chain, we can see here a Sankey diagram that we prepared where you can see the coke plant, sinter plant, pellet plant, blast furnace, and basic oxygen furnace. And what we've done here is mapped out the flow of carbon in the value chain. And the green lines, we can see the potential uses. So we can use a little bit of biocarbon in the coking blend, not too much, but a little bit. The main use of it is to use it as PCI substitute in the blast furnace. We can also use sized bio-nut coke, sized biochar, where we charge it in the iron ore layer to reduce the coke rate. And there's some other minor uses in the sinter plant, which Joe's mentioned, and the pellet plant as well. So when we accumulate all these things together, if you look at the arrow on the extreme right, there's potential to replace 50% of the carbon with biocarbon. Now, the reality is it's very difficult to get this biocarbon, as I mentioned, to the sites. And the pyrolysis technologies, particularly efficient ones that use all of the energy that's produced from the biomass, are very much at small scale now. So there's a few technical hurdles. But I think our opinion is there is a place for biomass in the reduction of CO2 emissions from the integrated steel plant. I'll pass it on to my colleague, Nick, who's going to talk about alternative iron units.
Yeah, thanks, Ian. So when we're talking about alternative iron units, really what we're talking about is metallic iron being charged directly to the blast furnace, in this case specifically scrap and HBI. And we have two graphs on this slide here. Starting with the graph on the left, this is essentially just a simplification showing the impact of increasing the metallization of your burden. That's by replacing some of the iron oxide with metallic iron. And the two main impacts that you get an increase in production from increasing your metallics, as well as a decrease in coke rate as less reduction is required, and that decrease in coke rate translates to a reduction in CO2 emissions. The figure on the right is digging a little bit deeper into the impact of charging metallics. And in this case, we're going back to looking at the operating windows, where as you increase the amount of metallics you're charging to the blast furnace, your operating window does shrink a little bit due to the change in the energy balance within the furnace. So you need to adjust your natural gas injection rate and your oxygen enrichment in order to accommodate those the higher amount of metallic burden that you're charging to the furnace. But I guess going a little bit further on metallics use in the blast furnace, one thing we do want to emphasize is that this is currently being done today. As was shown in the last slide, the AK Steel in the US has been doing it for quite some time. And also in Europe, voestalpine has done some work charging HBI to their furnaces located in Austria. So this was an analysis that we did at Hatch, where we looked at some of the public information that voestalpine shared on their results from charging HBI. And looking at the waterfall chart from the left, they started from their base case operations with no HBI, charging an emission intensity of 2166 kilograms of CO2 per ton of hot metal produced. And then by charging 100 kilograms of HBI, they were able to reduce their coke rate quite a bit, which resulted in emission reduction in the blast furnace itself, as well as in the coke ovens from producing less coke, as well as they were replacing the sinter in their burden with the HBI, so they were able to achieve a emission reduction in their sinter plant as well. And looking at the integrated steel mill in Europe on its own, they were able to reduce their emissions to just over 2,000 kilograms CO2 per ton of hot metal, which was about a 6 to 7% reduction. However, when looking at the full value chain, you need to account for the additional emissions to produce that HBI, as well as the pellets that are fed to the DR plant. And by accounting for those additional emissions, about half that emission reduction was given back. So, as this develops and hydrogen is used for DRI production, a larger portion of this emission savings can be realized. However, one thing that we wanted to reemphasize that this technology is being used today, and it does have promising results for marginal emission reductions. So with that, I'm going to pass it back to Ian to talk about electrification.
What you see in the picture is a hot mixer design that Hatch studied quite a bit, maybe 6-7 years ago. So in blast furnace operations today, we heat the hot air up to a certain temperature, and then we add cold air to bring it down to the hot blast temperature. So it's a built-in inefficiency that exists. So what we looked at, if you look at the image on the left, is a hot 4-finger hot mixer, and the red images are plasma torches that we would insert instead of injecting cold air to control the temperature, we'd inject hot air and increase the temperature slightly. And what we could see from the design in the middle is that the penetration from the plasma torches into the hot blast main is quite good. And if we look 5 meters downstream of the torches, we had a quite uniform temperature going into the blast furnace. So it was an interesting way to get rid of an inefficiency and to use green electricity. When we look at the waterfall diagrams, so you can see here, for 2 cases, the waterfall diagrams show the starting blast temperature of 1168 and the changes that we can achieve using a hot mixer. one going to 1250, the other going to, the graph on the right going to 1300. In this particular case, we weren't actually that interested in, at the time, greenhouse gas emissions. We were more interested in replacing coke. So if we look at the starting point, the 1620 was the emission rate from the blast furnace system. And then by using the hot mixer and increasing the temperature from 1168 to 1250, we could reduce coke consumption by 83 kilograms of CO2 removed. And we don't make the coke, so an additional 12 kilograms. But in this particular case, we used PCI to make up for the shortfall and the power for the torches. The power is, we used a fairly high grid factor, 0.68. So that could be reduced by, depending on where you are, but you could also purchase green credits through a virtual purchase power agreement. And if you use natural gas or green hydrogen, the PCI change here, the 65 would be reduced to half with natural gas and to 0 with green hydrogen. So we do have the potential to reduce the emissions. As here it's shown only by 20 kilograms, but we could probably reduce it by closer to 80 kilograms with some future changes. And of course, if we go to a higher temperature, these benefits, 1300 degrees, these benefits just become larger. The really big changes that we can see going forward are through the transformational technologies. And Nick is going to go through those with you now. Well, excuse me. We just wanted to compare the machines that we know. So plasma heaters, their plasma by definition is a very high temperature. It's 5,000 to 8,000 degrees. So if you use plasma heaters, Joe mentioned them being used in pellet plants, you do need to make design considerations to protect the refractory. Electrodes typically have to be replaced every 1,000 to 2,000 hours. Because of the very high temperatures, there's NOx generation. There is limited experience we learned from the plasma torch community of injecting plasma into pressurized environments, also using combustible gases. And the units are between 2 and 4 megawatts, but they are modular. It's a scalable technology. The other technology we looked at were resistive heaters. These are like your toaster or your hair dryer, wires that are heated up. And the advantage is there are several pluses to this. We can't get as high in temperature, about a maximum of about 950 to 1,000. The heaters have very long life. They're measured in years. Because the temperature is lower, the NOx generation is much less. They are commonly used in pressurized systems today. They're used for testing airplane engines, for example. Under development right now are syngas heaters by both Midrex and Energy Iron using resistive heaters. Lots of experience, and the modules are bigger. So these are two tools we are quite sure there are many ways that we can use these in the value chain from iron ore and coal to hot metal. The key is you need green electrical power. On that note, I'll pass it over to Nick, who's going to talk about transformational technologies.
Yeah, thanks, Ian. So we're talking about transformational changes. What we're really looking at is trying to find a way to get near zero emission steel produced through the blast furnace route. And in order to accomplish this, we really need to consider top gas recycling as a change in technology. So on this slide here, I have the figure published from the ULCOS trials that were the ultra low CO2 steelmaking program that was done in Europe in the early 2000s. And they trialed top gas recycling on the experimental blast furnace in Sweden. I'm not going to go through the flow sheet in detail, but essentially they had quite good results from those trials. They were able to get a 24% carbon reduction. And that was without considering sequestering the tail gas that was produced. However, because they were looking for a technology that could get up to a 50% reduction, they didn't pursue this further. However, in more recent times, the top gas recycling blast furnace concept has been picked up by Baowu in China, and they've been revisiting this with a very similar configuration to what was done in the ULCOS trial. However, they added the addition of more hydrogen or hydrogen-rich gas into the separated syngas that's re-injected in the furnace in order to reduce the emissions even further than was achieved in the ULCOS trials. And in this case, some of the results have been limited in their publication, but they're trying to get up to a 30% carbon reduction before considering carbon capture and sequestration from the CO2 scrubbing unit. And this actually pairs quite nicely with some analysis that we did at Hatch in 2019, where we were also looking at how you could achieve near zero emissions from a blast furnace steelmaking operation. And we came up with the hydrogen top gas recycling blast furnace concept, which is quite similar to the Highcroft project being done by Baowu. And the figure on the right is quite a bit going on, but it was essentially our configuration of what this could look like. And at the time, we weren't 100% sure what would achieve those yellow boxes, which was the CO2 removal and the heater. However, over the past 5 years, we've seen a lot of the technologies develop that can help achieve these requirements. For the CO2 removal, we had looked at getting a 100% pure tail gas stream. Well, that's probably not possible. Getting up to 99% shouldn't be an issue. And in terms of heating the recycled gases in order to inject them back into the furnace, as Ian just discussed in the last section, there's been a lot of development in electrical heating technologies that can be adapted for this. And if you have green power, that's an emission-free way of heating up your gases. So looking at this concept, what we found was that before considering um, carbon capture and sequestration, we believe we can get up to a 54% reduction in emissions just from the blast furnace itself. And how that was achieved was by fully replacing the PCI that was injected into the furnace with the recycled syngas and hydrogen, and about a 30% reduction in coke. And I guess what we wanted to highlight here is that in order to really get close to near zero emission steel produced in the blast furnace, a more transformational change is required to the blast furnace itself. And we think top gas recycling is the best option for that. So with that, I'll pass it back to Ian to close out our presentation.
In summary of what we've brought to you today, in terms of alternative fuel injectants, you can use direct hydrogen injection, but the amount of CO2 reduction you can get is limited, and the hydrogen is quite expensive, and it's inefficiently used in the furnace, as the utilization is only about 40 to 45%. Biochar can reduce emissions. There is a significant opportunity, but its availability and the technology to pyrolyze the biomass needs to be improved. Scrap and HBI additions are currently being used. They do reduce emissions, and the use of these ferrous materials should grow. Electrical technologies, plasma and resistive heaters can be used to enhance CO2 reduction strategies, and there's numerous places in the value chain that we can apply these. But the most important thing is top gas recycling. It's a really great opportunity to reduce blast furnace emissions. And the one thing is that a top gas recycling furnace can leverage all of the items mentioned above: hydrogen, biomass, scrap, and electrical technologies. On that note, I'd like to thank you for the time you spent with us today, and I hope you enjoyed these comments.
Thank you, Ian and Nick. Very comprehensive presentation. And we have several questions. We may not be able to answer all of them, but you can then type the answers in the Q&A for questions that we cannot take as of now. First one I'll ask is from John Lichtenstein. Nippon Steel recently announced 30% CO2 reduction from hydrogen injection in their experimental blast furnace. This probably implies more than 25 kilograms per ton of hot metal injection. Any thoughts?
We were able to estimate up to 35 kilograms, but our comments were that the operating window gets narrower and narrower. It comes down to the skill of operation, the instrumentation of the furnace. It certainly is possible. It just needs to be a real well-controlled operation. And the challenge for the blast furnace operators is always to get to that point, and it's a question of how close you can get to it. So we did estimate 30 to 35 kilograms in a normal blast furnace.
Okay. The next question is from David Marshall, and it's probably on several attendees' minds. Each one of these methods of reducing CO2 has different CapEx and OpEx associated with it. So which one do you think would give the biggest bang for the buck for CO2 reduction?
I think you can offer your opinion, Nick, but we're always of the view it's the top gas recycling blast furnace. There's some stages that you can go through. It is possible you may be able to leverage some third-party third parties, for example, for carbon capture. So we think that's the one. The others are quite incremental, but the real change comes through transformational change to a top gas recycling blast furnace. I don't know, Nick,
Yeah, I guess I would just add it. It's really tough to say on a general rule, as we believe that there's going to be some geographical implications for different technologies. In areas where you have more biomass availability, transportation becomes quite a bit smaller and your costs go down. If you're in an area with the ability to sequester carbon, that becomes more promising. Whereas if you're in a region with no good geology, then it's not as good of an option. So you really have to look at each case on its own to understand what the best technology is for that specific application.
And to that point, we've seen a number of announcements about using biomass in the Indian steel industry, which probably makes good sense there.
Yeah, thank you. The next question we'll take is from Stephanie Netopi. From the flow sheet that you showed about different places where biocarbon can be used, which location is the best for the biocarbon, and also what limits biocarbon use?
So the best location would be to replace PCI. There's certainly been trials done on normal blast furnaces, on charcoal blast furnaces in Brazil. Injection of charcoal is quite common. So that's the biggest opportunity. We don't need to process the biomass as much. I think one of the key things is, where do you process the biomass? If you can do it at the steel plant, you can use the gas for general heating purposes within the steel works. So, but the biggest opportunity for sure is replacing PCI.
Excellent. Next question from Angelo Manenti. This is for Nick. Is the hydrogen used in Thyssen's blast furnace green or blue or gray? And how much hydrogen was used in that trial?
So the trial itself was gray hydrogen, just because that was what's available. I think the goal of the program was to demonstrate it as a viable technology, and then find a way to secure green hydrogen in the future. In terms of how much was used, they did 2 sets of trials. So the first one was just injecting on one tier, and I think that was about 1,000 normal meter cube per hour. And then they did a larger trial, or they were planning a larger trial on all tiers, and I think that was going to go up to 25,000 normal meter cubes per hour. So when you're talking about so Thyssen's furnace in Germany is quite a large furnace. When you're talking about 20 kilograms per ton of hot metal, the amount of hydrogen you need does get quite large very quickly.
Next question we'll take is from Fernand de Dion. Does it make sense to use basically metallic materials such as hot briquetted iron in blast furnace? Isn't electric arc furnace more efficient for CO2 emission reduction?
So I think the CO2 reduction comes in the making of the direct reduced iron in the first place. So I think that the argument could be the benefit is the same. You do have the advantage in the electric arc furnace, if it's beside it, that you cannot charge the DRI hot, which is not so easy in most blast furnace cases. You couldn't charge it hot anyways, wouldn't go through the charging system. So that is a plus for the EAF. But I think the nice thing with the blast furnaces is the ability to consume great amounts of any kind of metallic material. So that's a plus. But I think we're going to find different strategies for different companies and the position they have in their supply chain to get the DRI. We do always say scrap is better than DRI. There's FEO and DRI. There isn't in scrap. So scrap is your first choice, but DRI is also effective at reducing emissions. Yeah.
Another question. This is from an anonymous attendee. Do you have data on the cost of these various technologies for CO2 reduction? Possibly a table of the additional capital and operating costs per reduction of CO2 will be useful.
We presented materials that's been developed over almost 9 or 10 years. And in those publications, we have presented operating costs for sure. Some of the capital costs, because the technologies are so new, either we didn't have a number or we didn't think the number really made any sense for these sort of discussions. But if you search through AIST's library, you can find most of those papers tagged with my name.
Yes, and I agree. It's highly specific to raw materials used and the facilities each place has. So Nick and Ian, thank you very much for your presentation. I'll hand it off to Joe More now to introduce next speaker.
Yep, thank you.
Awesome, guys. Nice work on that presentation. We have another great presentation for you from Brian Black from SMS. So Brian Black is the Vice President of Coke and Iron Processes from the SMS Group. He lives in Chesterton, Indiana, and he earned his BSIE from Purdue University in 1988. His work career includes working at ArcelorMittal Inland Steel as an industrial engineer and progressive blast furnace operations positions. He finished as division manager of Indiana Harbor 5 and 6 and division manager of Indiana Harbor Works 3 and 4 blast furnaces. From 2013 to 2019, he was an international consultant for the blast furnace process and operational support, technical support and training, recoveries, blow down, blow in, relines, interim repairs. From 2019 to 2022, he's worked with Paul Worth, SMS, as the VP and General Manager of Operations in North America. And from 2022 on, he's currently with the SMS Group. He is active with the following associations: the Western and Eastern States Blast Furnace Coke Plant Association and the AIST current iron making chair and past vice chair and papers chair. Brian.
Yes, coming, Joe. Thank you, Joe. Can you everybody see my screen?
Yes, looks good.
Okay, this section will highlight potential pathways for transitioning of top gas recycling. The following slide provides some background in the baseline for the discussion. How do we bridge gray steel or CO2 intensive to green steel? As we look at the transition, we begin to understand the playing field as policy, economics, and influence, which often dictate decision-making. Many of these factors serve as decision-making tools as they relate to regionality. When we look at the primary and secondary routes for steelmaking, not only here in North America, elsewhere around the world, we begin to bookend for our individual plants where they lie for the CO2 footprints and where improvements can be made. As a basis for our discussion, the process produces CO2, but on differing levels. Blast furnace route, basically, you've got 1.91 tons of CO2 per ton of crude steel. The direct reduction route, basically 0.61 tons of CO2 per ton of crude steel. And for the recycling route or the scrap route, basically a shade under 0.1 ton of CO2 per ton of crude steel. And this assumes basically green electricity. If we look at the iron and steel making from 1980 through projected 2050, essentially in the early 80s, there were a lot of other processes, and they had a larger footprint in the percentage. Most of those have gone away because of the efficiencies associated with them. Also, the EAFs had transitioned from basically being within the integrated plants to more of individual standalone producers. EAFs have grown incrementally, while blast furnaces over the same time period have grown greater than threefold. And that kind of relates back to what Joe talked about as introduction. From current day, steel production will grow to increasing population and per capita, mainly because of developing countries, infrastructure needs, natural disaster, world conflict, and also will need renewable energy needs. Secondary steelmaking will increase due to higher scrap availability and also focused usage of that scrap. However, primary steelmaking will still be required. The DRI routes are expected to increase strongly to 5-fold from today's production levels. Some new processes will come up. However, the thought there is that they will be not a huge player. They will be a player, but not a huge player. Those include things such as fluidizing beds, complete electrification of the iron production. In consequence, we can see that blast furnace prominence has grown since the early 80s and will continue its role in steel production after 2050. So it's really our duty and ambition to decarbonize this process and production route if we want to meet the climate goals of 2050. So when we look at actually turning this 2050 into more of a green, a lot of it's going to depend on electrical infrastructure, the competition for the renewable electricity, increased demand for high quality scrap, increased demand for the natural gas, and also nuclear footprint and growth. I'm not going to dwell a lot on this because Joe talked about this earlier within the webinar. But essentially, we have to look at iron ore pellet availability, the high silicas. We've also got the lump ores. We've got the beneficiation curve here on the right-hand side, which basically shows that as we go from the blast furnace BOF route, DRI OBOF route to the DRI EAF route, we have to increase beneficiation. And essentially, when you look at it, there's a high amount of residuals. There's also the environmental impact with basically 1 ton of BF pellet feed equating to essentially 7 tons of tailings. So now that we looked at this, the remaining is basically the electrical side of it. Look at electrical production here in the US yields at about 60%, remain fossil fuels, shade over 21% is renewables, and the remainder is nuclear. If we include nuclear in the green equation, that puts us at about a 60-40 split between fossil fuels and renewables in the United States, with the need for growth and infrastructure to supply. If we look on a timeline dating back to the 80s, we're looking at a US base versus a world base. Basically, in the United States, natural gas has displaced coal. Nuclear remain relatively status quo, and renewables have increasingly displaced coal. On a worldwide basis, regionality plays a factor. However, with the exception of nuclear remaining basically status quo and oil a slight reduction, all remaining fossil fuels and renewables have increased in usage, with fossil fuels outpacing the renewables. Now, switching gears to decarbonization, within the conventional blast furnace, there's different pathways for this. Essentially, what we look at is, for the blast furnace route, is transformation of the existing blast furnace via modifications in the facility and process. The others are obviously direct reduction in open bath furnace and direct reduction in electric arc furnace, either with the use of natural gas or the use of hydrogen. So the typical plant setup for today, we all know what that is. In the middle is basically the blast furnace hot stoves, being fed by pellets in our sinter, coke from the pellet and sinter and coke plants respectively. Slag here in the United States, although there is some change there, nominally went to slag pits. Slag granulation as of recent has really picked up. All raw materials are shipped to the plant or produced on site. Basically, natural gas is piped, and basically the off gas is utilized for making of the electricity. So what's really possible in the future? You can see that within this diagram here that most of the described components before remain the same. The basic principle is to simply adapt the blast furnace to a new technology utilizing syngas producing syngas stoves to lower the carbon input to the process. For the integration of biomass in our wood waste, the integration of a pyrolysis plant and integrated steel plant can be added and utilized. Now let's look at the transformation in a stepwise approach. As a first step in the decarbonization process, essentially injection of syngas at the shaft, at the lower shaft, is the possible answer. So when we start with the step one, essentially what this allows us to do is increase the top gas temperature, which is now a limiting factor for maximum seasonal injection at the TWIR level. Requires O2 enrichment to maintain the raft, and the corresponding decrease the top temperature below boiling point loads the furnace with moisture. It also enables the use of more auxiliary fuel at the TWIR level, basically coke oven, natural gas, hydrogen, or syngas. It allows for a coke rate decrease, CO2 emissions and OPEX savings with the decrease in coke rate / PCI rate. Part of the reducing gas bypasses the cohesive zone, which will reduce the flooding risk when utilizing cheaper, lower grade raw materials. Essentially, you're able to reduce your natural gas by less than 10%, but your PCI basically can be reduced 25 to 28%. It's an add-on technology that does not impact the TWIR belt of the furnace. The syngas equipment, excuse me, can be installed during a normal reline, basically in the outage reline time frame. There are a couple needs. One need is to evaluate the furnaces to determine cooling requirements, and that's based on the current furnace lines, the cooling design, because you're going to have some heat load changes and sidewall heat load changes. The other point of interest here is that in the current condition of a lot of these stoves are required CapEx expenditures to rebuild or improve, and this could be a possible offset to the introduction of this type of technology. So on a simplified basis, the coke oven gas and blast furnace gas are run through a mixing chamber, a compressor station, through the syngas stoves. You can actually modify with hydrogen, and also is injected in the lower stack of the furnace. This allows for high temperature reforming, also allows for TWIR. We could also inject for the TWIRs. There's no catalyst, is utilized for the reformer. Can accept typical impurities of the BF gas and clean, excuse me, clean coke oven gas. Max in utilization of internal steelmaking gases, and no additional natural gas is required. So the dry reforming plant is essentially one checker stove that mimics a BF stove in terms of the height of the checker chamber. So this is basically a trial that's been done and completed to test the ability to dry reform blast furnace gas and coke oven gas. So I'll give a quick description of the pilot plant itself and some of the results that it's seen. So as I said, the pilot plant is simply a one checker stove that mimics the blast furnace in terms of the height of the checker chamber. The burner heating is blast furnace gas and combustion air. It was designed sectionally so as to complete testing of the material grades with waste gas temperatures of basically 965 C. The gas was produced and flared and quality tested. Due to the high gas temperatures for a full-scale design, the checker grids would be required to be ceramic, and higher grade alumina, up to 99% required in the high temperature zones. 70% would be sufficient in the lower zones. One note here, following the trial period, sections of the stove were dissected for testing of the refractory. With respect to fouling and chemical attack, indications were good with the initial design of the stove itself, or the trial pilot stove itself. So now as we look to, as a second step in the decarbonization process, the existing blast furnace is then modified to basically mimic direct reduction in EAF model as a single direct reduction in EAF, and model as a singular continuous electric assisted smelter. The existing syngas stoves from step one remain, and step two to require the remaining stoves become syngas stoves and replace the hot blast stoves themselves. So basically, the reducing gases would come from the reforming stoves. The reducing gases would be injected in the shaft and also injected in the twir belt of the furnace via plasma torch. Complete carbon capture would basically take us down to a net zero. So some comments here for basically a blast furnace of 4,000 meters cubed of working volume. Essentially, you're looking at around 8 syngas stoves would be required. A blast furnace of 3,000 cubic meters will be 5 to 6 syngas stoves. In terms of testing with syngas and the plasma torch, some lab tests have been completed at the 100 kW. Late 2024, 2025 pilot testing will be done with 2,000 kW, and in 2026, full-scale testing is planned. In terms of development, looking at top-fired stoves, basically for footprint consideration and minimization of the combustion chamber sizing, further development of purging between the blast furnace and heating cycles, and a split on the chimney side of the stove for introduction of fuels. Some quick, so basically when you look at the overall, essentially the top gas recycling reformed by natural gas and or coke gas. H2 can simply be fed to the reformer. Twir gas is superheated, basically 2000 C by the plasma torches. Nominally for PCI injection, raft is 2850 to 2200. Natural gas 1950 to 2050. With O2 utilized to increase the raft. With basically the plasma torch, you will have no blast, so there's little consumption of cold oxygen, no PCI, so no auxiliary fuel injection, and you can simultaneously inject syngas at the lower shaft. Utilizing natural gas, you basically got, with the process, you've got 43% CO2 reduction. Utilizing the hydrogen, you bump that to 61%. So really the target coke rate would be somewhere between 180 and 100 kg per ton hot metal. Some quick notes for clarity. Approximate residence time for hot blast stoves is 4 to 6 seconds, while the syngas and reformer stoves is 10 to 15 seconds. The twir velocity will be controlled with design and sizing of the new injection twirs. Drainage to the hearth should improve with less boss gas and flooding implications. Basically, shutdowns would entail purging of the injection systems as reduced. Target coke rates can be achieved as CO2 degradation of coke within the shaft of the furnace is minimized and the strength is maintained. Design of the graphite electrodes, as spoken in the earlier presentations, would revolve around the ability to change without a furnace shutdown. These two right here basically give us what, and this basically just shows the process flows associated with the 180 coke rate. You've got basically the injection at with the 320 kW at the twirs. Also, you have the injection in the secondary bustle pipe in the lower stack of the furnace. This equates to emissions of only 5% higher than the natural gas DRI OBOF route. If we go to the 100 kg, we have basically the same, where we're actually injecting the hydrogen with a higher kW plasma torch, and essentially only 47 kg or 2.5% less reduction in CO2 compared to H2. So if we move along, now that can we complete the same without green electricity and hydrogen locally? So in the proposal here is, what do you do in this case? So essentially the substitute to produce green energy by cheaper green energy would be imported. Since importation of electrical energy and our green hydrogen is not possible or very costly, the look here is now looking at ammonia and importing. It can be produced from hydrogen with very high efficiency. It is easily transported since it liquefies depending on the pressure above -40 C. Ammonia is already transported widely in the fertilizer industry, So how can we efficiently use the ammonia in the integrated steel plant? I'm not going to go through this slide, but essentially for vaporization, heating and cracking, the vaporization basically is utilized from the cooling water from the furnace, and the combustion is the blast furnace gas combustion. The blast furnace gas combustion with efficiency approximately for basically heat recovery. So this is possible slightly different setup. The difference here now is that you essentially set up an ammonia cracker utilizing the blast furnace gas as the heating source. This becomes completely electrically independent because you can actually use the top gas to produce your electricity, feeding your plasma torch. When you look at metallization testing was completed. The metallization was greater than 95%, utilizing basically the ammonia here to 62% CO2 reduction. With HBI or green HBI, you can move that up to 72. Now, this came up in previous slides. These numbers here are basically the economics associated with integrated steel plant. The comparison here in the slide is for CO2 abatement cost of basically the easy melt in an integrated steel plant versus the DRI OBOF route. In the graph, CO2 abatement costs, knowing that CO2 reduction potential is similar for both alternatives. In the dark blue is the OPEX cost, and light blue is the CAPEX, with an amortization period of 15 years. We've compared easy melt with the DRI on natural gas, highlighted in blue, and once using hydrogen in green, and then also with the ammonia. The units are basically shown up on the table over in the right. So when you look at it, the cost efficiency, basically for the primary green steel, CO2 price of 100 euros per ton can basically pay for natural gas. Easy melt, the transportation costs only for the ammonia, basically €1 per kg. And the H2 price differential between regions can easily pay for the transportation of NH3. The economics can of course further be improved with putting center as the iron ore source in these metal case. And that's basically due to the increase in the furnace. So if we look in terms of a summary, the uses of all types of iron ore, there's really no supplier dependency. We've got high flexibility concerning energy input source, high CO2 abatement, efficiency per H2 molecule. There's strong operational cost advantage. We've got strong CapEx advantage in brownfield projects. Uses steel plant setup. Majority of the stoves currently in use are needed rehabilitation. It's a low stepwise solution, not a no return solution. Specific CO2 emissions similar to the DRI OBOF, and net zero CO2 with smart carbon usage and storage. I appreciate everybody's attention. I think Madhu, I send it back to you.
Yes, thank you, Brian. A lot of ideas there for blast furnace folks to think through. We'll just take a couple of questions. We are kind of running to our final stretch. This one is from Richard Cum. How will syngas affect refractory and campaign life?
When you look at it, that's one of the tests that was being done with the pilot plant. As the scale up continues, those tests will continue. In terms of usage in the furnace, as we talked about basically what's happening with regards to the cooling mechanisms and the heat loads on the sidewalls of the furnace.
Okay, and then one other quick question. What is the minimal, this is from Jose Senra. What is the minimal quality of coke to sustain the burden inside the proposed blast furnace?
Nominally, the studies were done basically in Europe. So if you're looking at a CSR value somewhere in the neighborhood of 65%, stability somewhere around 63 to 64.
Okay, thank you very
And-
much, Brian.
Yeah, and
Excellent presentation. And
Thanks.
I'll hand things back to Joe Morey.
Thanks, Madhu. Charlie, you want to bring us on home with the last few slides there?
Joe, I'd be glad to. I want to remind everybody that this is the first of 2 webinars on the blast furnace topic. Please contact today's moderators if there is something you would specifically like to see covered in the next one. And requests for distribution of individual slide decks should be directed to each presenter. AIST has these webinars stored in the past webinar portion of the available website shown here. For a curated list of the previous 10 to 12 decarbonization focused webinars, please go to this webinar address and choose the View Now portion at the bottom of the screen. Ian mentioned that these papers can be found in the AIST Resource Center. Please sign in and use the keyword search for specific topics. AIST has a near future presentation of each of these in-person training sessions, all the way through the Corpus Christi, Cleveland, Ohio, Orlando, Florida, and Houston, Texas locations. We want to remind everyone too of the AIST Tech upcoming major conference in May of 2025. We want to thank you and Leckler for sponsoring and attending this webinar. Thank you all, and we'll see you at the next webinar.